Good day, everyone. This is Zen Programmer here. Thank you for joining today's session on feature scaling in data science. I'm excited to walk you through an essential yet often overlooked step in the machine learning pipeline: feature scaling. In this presentation, we will explore different types of scalars, why they are necessary, and how they can significantly impact the performance of your machine learning models. Whether you're new to data science or a seasoned professional, understanding how to scale features effectively is crucial for building robust, predictive models. Let's dive right in. Before we get into the specific types of scalars, let's first understand what feature scaling is and why it's important. Feature scaling is the process of standardizing the range of independent variables or features of data. Many machine learning algorithms, such as k-nearest neighbors and support vector machines, rely on distance metrics to make predictions. If the features are not scaled, those with larger ranges will dominate, skewing the results. Additionally, feature scaling helps models converge faster during training, particularly in algorithms like gradient descent. So, without proper scaling, your model might not perform as well or may take longer to train. The first scalar we'll look at is the min-max scalar. This technique transforms data to a fixed range, usually between 0 and 1. It works by subtracting the minimum value of each feature and dividing by the range, which is the difference between the maximum and minimum values. This scalar is particularly useful when your data doesn't follow a normal distribution or when using algorithms like neural networks and k-nearest neighbors that are sensitive to the scale of the input data. However, one drawback is its sensitivity to outliers. If your data set contains extreme values, it can distort the scaling, so it's best used when the data has a known range. Next up is the standard scalar, one of the most commonly used scaling methods. This scalar standardizes features by removing the mean and scaling to unit variance. The result is that each feature will have a mean of 0 and a standard deviation of 1. This type of scaling is particularly effective when the features follow a normal distribution. It works well with algorithms like linear regression, logistic regression, and SVM, which assume that the data is centered around the mean. However, for skewed data, this method may not perform as well because it assumes a Gaussian distribution. The robust scalar is designed to handle outliers better than the previous scalars. Instead of using the mean and standard deviation, it uses the median and interquartile range, making it robust to extreme values. This scalar is ideal for data with many outliers or heavy-tailed distributions. The downside is that it may not perform well with data that has a normal distribution, as it does not center the data around the mean. The Max-Ebb scalar is a type of data scalar that changes the values of your features based on the largest number in each column. It works well for data with lots of zeros, like when working with text data that's been turned into numbers. This scalar keeps the zeros and doesn't fill in gaps, making it a good fit for specific machine learning methods that prefer this kind of data. However, it's not the best choice if your features have very different ranges, as it might not handle those well. The quantile transformer scalar is a powerful tool for transforming data to follow a uniform or normal distribution. It uses quantiles, which are points in your data distribution, to map the data to a desired output distribution. This scalar is particularly useful for highly skewed data or when you need a Gaussian-like output for models that perform best with normally distributed input features. One downside is that it can distort linear relationships between features, which may affect certain models. In the code example, we'll see how this scalar can be applied to reshape a skewed feature into a normal distribution. The power transformer scaler includes two types, Box-Cox and Yeo-Johnson. Both methods aim to stabilize variance and make the data more Gaussian-like. Box-Cox can only be applied to positive data, while Yeo-Johnson can handle both positive and negative values. This transformation is useful for reducing skewness, making it easier for linear models to learn from the data. However, it's sensitive to outliers, so it's important to consider whether this method is suitable for your dataset. With all these options, you might be wondering, how do I choose the right scaler for my dataset? Here's a quick decision guide. If your data follows a normal distribution, go for the standard scaler. If it has a predefined range, use the min-max scaler. For data with significant outliers, the robust scaler is your best bet. For skewed data, consider the quantile transformer or power transformer. If your data is sparse, the MaxAb scaler is ideal. Always remember to experiment and validate the performance of your model after applying different scalars. To wrap up, feature scaling is a fundamental step in the data preprocessing pipeline that can greatly influence the success of your machine learning models. By choosing the right scaler, you can ensure that your features contribute equally, avoid biases, and help your model converge faster. I encourage you to try out different scalars in your next project and see how they impact your results. Thank you, and see you next time.